Welcome, everyone, to today's program, Over the Horizon, Finding the Future of Semiconductors. My name is Lindsay Maychek from FedTech, and I will be your host and moderator today. Again, thank you for spending your time with the Lab Innovation Networking Center. So if you have any connection issues with Zoom or your computer, the best thing to do first and foremost is just to restart it. That usually alleviates any of those issues. If Zoom were to go down for any reason, we will record and still share this publicly on YouTube. The whole session is being recorded, so you will be able to watch anything that you would miss. So fear not. The event may be rescheduled if there's any major technical issues, but that won't happen, but we have to make sure to say it just in case. So a quick few webinar tips here before we get into our program today. The Q&A session is open. So you see the Q&A button at the bottom of your screen. It looks like two dialog boxes on top of each other. Use that to ask us questions throughout the program. Our panel here is excited to hear from your questions. So please use that feature throughout. Ask the lab representatives anything and everything here. We are standing by to answer them. You can also use the thumbs up button to upvote questions and answers that you want answered. So use that thumbs up to bring them to the top of the queue. Lastly, for audio settings, you can adjust the volume of sound here by clicking that up caret on your audio settings next to the microphone. If you can hear me, that means your audio is joined, however, but feel free to adjust those settings as needed. Okay, so enough housekeeping. Let's get into our programming. This is an event by the Lab Innovation Networking Center, a collaboration between the 4 Bay Area labs, SLAC National Accelerator Laboratory, Berkeley Labs, Sandia National Laboratories, and Lawrence Livermore National Laboratory. This regional innovation cluster from the DOE National Labs is designed to foster those collaborations between you as industry and the labs themselves. So on today's program, we're going to kick it off with a technology showcase. You're going to actually hear from all 4 linked labs with specific cutting edge technologies in a 1 to 2 quick pitch, exciting format. And then we'll have over the horizon panel discussion. So both lab and industry experts coming together to discuss about what comes next and what is the future for semiconductors. So what's in it for you? Why should you partner with one of the Lab Innovation Networking Center's labs or the DOE in general? You can see this list here. We won't go into them, but just throughout the program today, you're going to see a lot of non-intuitive ways that you're going to be able to partner. So in the back of your head, think, how can this benefit me? Because there's a lot of different ways that you can connect and a lot of different mechanisms to do so. So at this time, I'd love to introduce Ms. Mary Monson, the Senior Manager of Technology Partnerships and Business Development in Sandia National Laboratories, to provide a quick background and understanding of how Link can benefit your business. Mary, welcome to the stage.
Thanks, Lindsay, and welcome everyone. As Lindsay mentioned, there are ample opportunities to partner with the 17 Department of Energy National Labs. The lab complex is nationwide and large, so it can be difficult to navigate. You could ask yourself, where do I even start? As a business, your time is a precious resource, and we certainly recognize that. Thus, Link was created to provide a front door to not only the regional labs in the Bay Area, but across the lab system. For example, as you see here, we'll be able to connect you with specific technology areas at each of the labs, and the connection goes both ways. Coming later in the program, you'll see examples of lab technologies looking for partners. Each lab has its own unique capabilities that could help your business, and Link is here to point you in the right direction. Beyond that, though, think of Link as a multiplier. You could access research experts, unique capabilities and facilities, and innovation from one national lab. But why not engage 4 at the same time? I want to emphasize a key word listed in Link's mission: resource. The Lab Innovation Networking Center for Industry in the region provides a simple value proposition: more access in less time. As technology transfer professionals, we want to work with you to bring lab innovations into real-world applications, or even co-design the next transformative technology with you. Using Link as the front door to partnerships with labs gets you there faster. One tangible example of Link's streamlined goal is the 4-lab Link non-disclosure agreement. This document applies to Sandia, SLAC, Berkeley, and Lawrence Livermore. one document for all 4 labs, saving time and paperwork during the critical initial discussion phase. In addition to being the central access point, we aim to provide helpful resources along the way. For example, the deep dive panel discussion later today will provide insights in how labs and industry can work together to find solutions to America's most critical challenges. Today's Over the Horizon event is specific to microelectronics and semiconductors because the topic's importance is recognized by the Department of Energy, its national labs, and industry. We want to continue to find novel approaches and pathways to partner. If you take anything away from this event, please let it be that all 4 labs want to partner with you, and it all starts with a conversation with Link. Right now, these conversations are virtual, but we hope to soon be able to host in-person meetings. I'd like to introduce Matt Garrett, the Director of Technology Transfer and Private Partnerships at SLAC National Accelerator Laboratory. He'll share more information about Link's physical location. Thanks, Matt.
Thanks, Mary, for the introduction. On behalf of SLAC and Stanford University, we'd like to welcome everyone to today's program. SLAC is excited and proud to host the physical location for Link. We're situated on 450 acres on the west side of Stanford's campus in Menlo Park, California. The location is centrally located in the Bay Area and within accessible driving distance to each of the other Bay Area labs and each of the nearest major airports in the Bay Area. The goal for this physical location is it will act, as Mary said, as a front door where the private sector and other potential partners can engage with researchers and tech transfer professionals from the Bay Area laboratories. The location will have meeting spaces, a conference room, and will have the ability to facilitate both face-to-face and virtual meetings. We at SLAC and all the other Link Bay Area labs are excited about the possibilities that this location will lead to in engaging with the private sector and forming partnerships to help advance technology and provide solutions to the technical challenges that industry is facing. I want to thank you for attending today's event, and we look forward to hosting meetings here in the future.
Thank you, Matt, and thank you, Mary, for the introduction. It's exciting to think about being able to meet in person and connect in person. So I know I'm excited to visit the Link location at SLAC. So let's position now and head into our technology showcase, right? What's the context of why do we want to do this? You can see here this quote from the Secretary of Energy herself. Microelectronics are the key to technologies tomorrow. We see these in every aspect of our daily life, and it's something that's a major focus for the current administration and the Department of Energy as a whole. So now you're going to be able to hear those cutting edge technologies directly from the scientists themselves that are working on them in the labs. And something that all of these scientists and all of the technologies that you're going to see today have in common, well, they're looking for industry partners like yourself. So if at any point throughout the program you see a technology that you want to engage with and partner with, info@bayarealabs.org is going to be that email that's going to connect you directly to them. So let's jump in the quick pitch format. The pitch is only about 1 to 2 minutes, so very, very quick. I know I'm sure you've done pitches to venture capital firms before or potential investors. This is a little bit different. We're flipping it on its head, 1 to 2 minutes from the scientists themselves. And then we'll have a quick Q&A, just one question per pitch, moving on after. So that being said, with the format, let's head in and meet our first quick pitcher, Rob Panis from Lawrence Livermore National Laboratories. So Rob, the floor is yours, or Bob, excuse me, the floor is yours for your quick pitch. Take it away.
Thank you very much. Okay, so my name is Robert Panis. I work at Lawrence Livermore National Laboratory, and I'll be talking about solid state beam steering. Okay, thank you. Now, innovation in the RF domain has enabled Wi-Fi, weather mapping, radar to land planes safely. However, an increasing demand as time has gone on is for these fields to move to a higher capability, to a higher resolution, higher data rates. All of this requires them to move to smaller wavelengths. from the centimeter scale domain of the RF of the RF waves to the micron scale wavelengths in the optical domain. Unfortunately, while the RF field uses electronic beam steering, optics are still largely stuck with 1940s mechanical steering, gimbals, and telescope systems that are large, heavy, and slow. They also tend to be fairly fragile. The light field directing array was designed to provide that critical enabler to replace the analog beam steering in the optical domain with what's already commonplace in the RF domain, the electronic beam steering, so that we can enable large-scale transfer of technologies from the RF capabilities into the optical domain. Things like improving sensor resolution and improving data connections between satellite megaconstellations with solid-state optical comms. Also upgrading LiDAR units for solid-state LiDAR units that can adaptively scan areas instead of simply spinning state systems, and augmented or AR/VR displays. Next slide, please. Our approach draws on existing and next generation technology. So we look at gimbals as the existing technology, which, as I mentioned, these are precision motion systems that are large and slow, but they provide that critical feedback control so you know where you're pointing. So you can gain very high resolution maps of areas and systems. On the other hand, the emerging technologies, optical phased arrays at the bottom left, these are incredibly small, they're incredibly cheap silicon type systems, but they're, and with that speed, unfortunately, tends to come along significant unreliability. So it tends to be difficult to get the kind of precision motion that gimbals can achieve. Our approach on the top right here uses an array of micromirrors to operate as miniature gimbaled systems over a large aperture that allows us to do precision motion. We run each in a closed loop operation that's like a conventional macro scale gimbal, but with the speed of an OPA. So this lets us draw on the strengths of both domains to provide a system that can steer a beam across large ranges of motion in microseconds at hundreds of thousands of degrees per second, split and recombine beams to parallel scan areas, or to make multiple connections per second in satellite megaconstellations for dense optical connections. This is enabling us to do that transfer of technologies from the RF domain into the optical to provide hundreds, if not thousands of times boosts in terms of data rates and resolution benefits. We're spinning this technology out from Livermore with a commercial partner, Bright Silicon Technologies. Now, BST will only produce the chips. We're looking for strategic partners in the wide range of fields in which folks are interested in upgrading their capabilities to generate next generation products that utilize solid state beam steering gimbal on a chip capability. We've recently this summer won the DOE TCF award for $1.5 million to start producing these MEMS chips in the next 16 months. And BST is in talks with companies that are interested in exclusivity in the field in return for the final $2 million NRE that we need to finish covering the packaging to produce these first article prototypes by the end of 2022.
Thank you, Bob. Much appreciated. So if you have any questions, you can use that Q&A feature to ask your questions, but we have to keep moving here pretty quickly through. So Bob, I'll ask you, you put that call out looking for partners. Why is that something that's so necessary to get this technology out into the world?
Yeah, thank you. So we're at the point of a large bump as we move the technology. This is the tail end of about 10 years of development, and we're moving the technology out into a foundry where we're doing the final closeout on all the capabilities so that we can provide these package chips where users can finally get a sense of what's possible. This is a unique enough technology. It's a smart mirror instead of a conventional large scale mirror that you're either just going to lock in place or put on a very large gimbal. And there's a lot of new capabilities that require people to sort of lean in and get their hands on it to understand what's possible. So we're finding that we really need to make that jump out to get the product in the consumer's hands, to get that into those strategic partners' hands so that they can figure out how do you make most use of this for next generation product.
Perfect. A perfect bow on that. So thank you so much for your quick pitch. I know it was hard and it's challenging for all the scientists that you're going to see today to get this very cool technology into a minute or two, but great job, Bob. And I'm sure that a lot of folks will be reaching out. Again, info@bayarealabs.org. So our next quick pitcher comes from Sandia National Laboratories, Benjamin Feinberg. So Benjamin, welcome to the stage. You are in the hot seat now for your 1 to 2 minute quick pitch. And here you go.
Great, thank you. So I want to talk a little bit about some of our work on how do we go from interesting analog circuits up to algorithms that can be used in real products. So I want to focus on two applications that we've been looking at a lot over the past couple of years. First is this analog matrix inversion shown on the left, What this is, this allows us to invert a system of linear equations, do a matrix inversion, a computationally hard problem, in a single analog step. And the advantage of using this analog system is this potentially enables order of magnitude energy and latency improvements over digital systems without necessarily losses of solution quality over digital approximation methods. We're currently testing a 32 by 32 prototype of this system on using GlobalFoundries 45 nanometer process. And if you'd like more information on this, please consult our HPCA 2021 paper on analog preconditioning for large-scale iterative systems. Another thing we're working on here is on the right-hand side, we have this NAND flash-based ternary content addressable memory structure. The advantage here is that the idea here is that using a standard NAND flash array, we can do highly parallel bulk search within a storage device. The advantage here is that we're moving our computing all the way into the storage array, so we can leverage the vast density of NAND flash, as well as also potentially providing order of magnitude speedups based on our initial simulation results for bulk parallel search inside storage. This is ongoing work, and we're currently looking at applications for both structured data, so like database applications, unstructured, and then unstructured data like you might find in sort of NoSQL databases, and more generally unstructured data overall. And we're looking for commercial partners to help us bring these ideas to market.
Great job, Benjamin. Thank you so much. You were definitely under that minute, so well done there. In the terms of timing, I've been joking with them. I wasn't going to use the hook, but everybody stayed well into time, so a lot of information coming out. So, Benjamin, what do you think is one of the biggest challenges with your technology in terms of why you need an industry partner here to get this out of the lab?
So the biggest challenge is that there's a lot of complexity in sort of going from bringing these analog systems online. As we've been experiencing with some of our work on our prototype of the solver, there's some very interesting sort of quirks related to how applications have to interact with some of these systems. And so this is the kind of thing where we need expertise. We need expertise from industry with analog designers who can really help us tailor what we can do with their process expertise.
Great, thank you, Benjamin. That's a theme that I think that we're going to see throughout all of these quick pitches. It is a way more collaborative environment than I think a lot of people realize. So thank you, Benjamin. Again, info@bayarealabs.org if you want to reach out and hear more. So now we'll move into our next quick pitcher, Anne Sacknwat from SLAC National Accelerator Laboratories. So Anne, welcome to the stage here. We are excited to hear all about NanoX.
Thanks, Lindsay. So at SLAC, I lead the NanoX group, which is a group that explores the interface of nanotechnology and a wide range of sciences, including materials, energy, quantum, X-ray, biology, and chemistry. One of the things that we're developing are on-chip micro-scale supercapacitors for self-powered IoT devices. Self-powered IoT devices are useful for applications such as implantable sensors for healthcare, maintenance-free sensors for remote areas, or extreme environment sensors for space. These devices need an energy storage solution that have high power density, fast charge discharge rates, and long cyclic stability. They also need to integrate well with energy harvesting technology. We have developed a scalable high aspect ratio hierarchical etching method that has enabled us to build a 3D micro supercapacitor device. In this image, there are 1 micron wide nanoporous pillars etched over 500 microns deep throughout the entire wafer. By coating these structures with a variety of materials using atomic layer deposition and optimizing these processes, we can use these structures to build a supercapacitor. The devices that we have developed currently have areal energy densities 2 orders of magnitude higher than what is commonly available at areal power densities of a few milliwatts per centimeter squared. We are also using these same high aspect ratio etching technologies combined with specialized surface functionalization to develop high sensitivity sensors. Next slide, please. Our group is also developing non-destructive high-resolution X-ray imaging for microelectronic devices. So the idea here is that with ongoing advances in fabrication capability, we also need a way to see and visualize what we make and to detect defects. Currently, the highest resolution 3D imaging techniques available, such as FibSem imaging, are destructive. An example of 3D FibSem imaging of a chip is shown on the left top corner here. By using X-rays, which are able to penetrate straight through a chip, we can think of applying some of the high resolution imaging techniques that we've been developing to microelectronics applications. So here's an example on the bottom left of an X-ray wavefront imager that our group has developed that has achieved 3 sigma sensitivities of less than lambda over 100 and accuracies of less than lambda over 100 at an energy of 9.5 keV. By using variations of this imaging method, we are working to develop metrologies at multiple stages of design and fabrication, such as materials and process development, nanofabrication, process control, and in operandum monitoring. Thank you.
Great job, and thank you so much. Again, that Q&A is open, so feel free if you have any questions for our team of scientists here, please use that Q&A. But Anne, my question for you, as you've gone through and you've developed the nanofabrication and you see all these applications, what do you think is the most likely use case for this as you move forward? I know it's in the X-ray imaging, but what do you think is the most likely application moving forward?
So for the supercapacitors, we are aiming to try to develop these self-powered IoT devices. We look forward to trying to being able to integrate those into real world type of devices. And for the X-ray imaging, we're really looking at different metrology capabilities all throughout the entire fabrication process for chip makers.
Great, lots of different options. So Anne, thank you so much for your quick pitch. We appreciate you joining us, Anne, all the way in from SLAC National Accelerator Laboratory. So from Sandia, now I'd like to introduce Alec Talon. So Alec, the stage is yours for your quick pitch here. Just a minute, good luck.
Great, Lindsay, thank you very much. So I'm Alec Talon. I'm a staff scientist at Sandia National Labs in Livermore, California. And over the past several years, we have developed a new kind of device, a new kind of non-volatile memory that we think is ideally suited for analog computing using post-CMOS devices. And specifically this ECRAM, that's electrochemical random access memory, is based on battery materials. And what we've been able to show over the past couple of years is that these devices can operate very fast, nanosecond speeds. They can be compatible with CMOS fabrication, and that they're really well suited for accelerators designed for operations like running neural networks, variety of neural networks. They can run in spiking or non-spiking mode. And I put up a couple of references if you're interested. You can also find this technology on Wikipedia, and you can find more references there. But just in a little bit more detail, these devices would go into crossbar arrays that would actually form the backbone of the neural networks. And they have electrical characteristics that are really well suited for analog computing in the sense that you can tune their electrical resistances up and down over a large range. They can store that value for a long time. And in simulations, you can see, and this is bottom left, that they indeed provide great energy savings and time savings compared to state-of-the-art CMOS-based technologies. Can I have the next slide? So in my second slide, what I'd like to say is that over the past year, we've demonstrated we can really go from materials that were originally based on lithium, because we started with battery type materials, which is not compatible with silicon, to materials that are completely compatible with silicon fabrication. And in fact, we have now demonstrated our first chip. It's just a 36 by 36 array. There are still many challenges, and that's one of the reasons we would love to partner both in scaling these devices from the micron size where they are now down to sub-micron dimensions, and understanding how these devices operate at these scale dimensions, and of course scaling to larger and larger arrays so that we can demonstrate processing more and more complex problems. Thank you.
Great job, Alec. Well done. Lots of information there. Loved all of the charts here. I don't see questions coming in, but please feel free to do so. So, Alec, I'll ask a question here in our short time that we have left. I know you mentioned that there were some challenges. That's why you're looking for an industry partner. But how does collaboration really help overcome those challenges in your experience?
So industry, particularly that is absolutely focused on electronics manufacturing, has the know-how, has the capabilities to address the kind of issues in scaling that we simply at a national lab and certainly at Sandia in California may not have as ready access to as somebody in industry.
Right, and that's initially early on with the technology to prepare so it can be manufactured. Right. So it's a really good point of emphasis there. Getting early on makes that transition a lot smoother. So thank you, Alex, for bringing up that important point. We appreciate it, and we appreciate your quick pitch. So again, info@bayarealabs.org to connect with Alex and hear more. So our quick pitch, our last quick pitcher, but certainly not the least by any means here, we have Peter Nugent from Lawrence Berkeley National Laboratory, who's going to be showing us two technologies in just about a minute, which is a tough order, but I know he's ready for it. So Peter, the floor is yours. Take it away.
All right. Thanks, Lindsay. So the two things that I'm focused on here are for microelectronic simulation. So basically, what we're focused on with first code Artemis is on 5G and quantum components. That's what we're working on now. And the Chambo code is focused on things that require complex geometries and multiphysics coupled systems. Think of these as codes to save you from trial and error. So you come up with a great design, you want to go to one of these labs, well, maybe you want to do design optimization first before they build something for you. And the benefit here is that these codes are scaled to run on high performance computing systems, and they perform orders of magnitude faster than commercial codes. So next slide. So this is the Artemis code. Artemis is a combination of two codes, WarpX and AMRX, focused on magnetoelectric, superconducting, and spintronic devices. That's what we focused on so far. It uses adaptive mesh refinement, as Chambo does as well, to basically take you down to the quantum level, but out also to the device level and capture all of that physics across that huge range in scale. Wonderful agreement with experiments and a great scalability on GPUs now for running these simulations. The next slide shows us the Chambo code. Chambo has been focused much more on complex geometries, so automated mesh generations for microelectronic simulations. And they can take these directly from CAD files or even volumetric experimental data like X-ray tomography. Great coupling of simulation to parameter studies, so you can do design optimization, bringing in some AI and ML solvers there. And once again, these codes scale to over 100,000 cores. And some examples here of everything from carbon fiber matrix nanostructure for fuel cells, heat transfer. What they were looking at here is removing heat from a CPU using new device designs. So all of this is possible, and many other things as well. And finally, on the last slide, I'd like to make a pitch for an easy way for industry partners to tie into our labs, and that's the HPC for Energy Innovation Program. The goals here are to accelerate innovation, lower energy costs, speed up the design, reduce waste, and shorten the time to market. This is led by Livermore, Berkeley Lab and Oak Ridge are major participants, but all the labs, SLAC and Sandia and many others work with us as well here. And it's a very simple program. Industry partner comes up with an idea. They work with a lab partner. They propose. Proposals are open twice a year. They support lab staff scientists to work on your problem. So we could take those previous codes and work on a problem with you in your specific area. And the benefits come out to you, and you get the computing time for free. So it's a great way to open the door to engage with us. Thanks.
Thanks, Peter. I have a very simple question because we are just at time here and we got to jump into our panel. But when we talked about the Armbrust computing for energy innovation, you were telling me the likelihood that it was to be accepted in. So can you just give me a little bit of a sense of the magnitude of how likely it is if you apply to this to get in?
So we typically pull in about 40 proposals each half year. And of those 40 proposals, this is just a 2-page write-up that we're looking at. We'll accept half of them to move on to a full proposal. And about 8 weeks later, you submit a 6-page proposal fleshed out entirely with your lab partner, and about half of those are accepted for funding. So just straight off the bat, you have a 25% chance of getting this, but if you get to the second stage, it's even better. And we love doing these, and we love doing it with a variety from small companies to the largest companies in the world. We love working with any and all. And the idea is to bring HPC to you because we're very versed in it. And we help you get to that next level with things that you probably can't afford to have in-house.
Well, thank you, Peter. I like those odds. I like the 2-page part of that proposal. So
makes it easy.
Thank you. So thank you for sharing. Info at BayAreaLabs.org will be able to connect you to Peter and all the rest of our quick pitchers. So thank you once again to everybody that shared their technologies and those cutting edge. Again, BayAreaLabs.org. So now with our time remaining, we are going to move into a panel. I've been really excited about this. Talk to each of our panelists individually to say, what are the main topics here of how do we find the future? How do we go beyond Moore's Law? How do we make sure that climate change and energy efficiency is involved? And I'm so excited now. I'll stop my screen share so we can see all of our panels in much higher definition and full screen. So Ramamoorthy Ramesh from Berkeley Lab, if you can just give me a tweet-sized little introduction to yourself and why you think you're on this panel, that'll kick us off today as we go through our roundtable here and meet our guests.
First, just Ramesh, don't kill yourself with my first name. All right. So second, I'm a professor in physics, material science, also a senior scientist at LBL. So, we're deeply involved. We've been pushing this for a while now with various people. So, and there's my partner in crime, Rick McCormick. How you doing?
Good. Nice to see you, Ramesh.
Yeah, that's right.
Been missing you.
Rick and I were tag team partners like 6 years ago. So kicking off this stuff we'll talk about today. So.
Yes, I used you both to say, oh, well, Ramesh, Rick is also going to join this panel. Well, Ramesh is going to join this panel. And that's how I got both of them together. But Rick comes to us as senior manager here at Sandia National Laboratories. And then those are our lab representatives. And from the industry side, we have Jeff Welser here, COO of IBM Research. So Jeff, can you give us a little tweet-sized background just so folks here at home can get to know you?
Yeah, so my background is in semiconductor devices and physics. And of course, IBM has been pushing that technology for many, many decades. So the lab I work in does everything from quantum to standard semiconductors to AI hardware. So excited to be here and talk about it.
Yes, thank you so much for spending your afternoon with us. And then Daniel, too, Silicon Catalyst, give us a little brief background. You have done many different roles across many different industry portions. So give us your tweet size. That's what I'm using here to describe it.
Well, at IBM, I made fabbed out the devices that Jeff designed. Then I got to lead the Semitech consortium, which did R&D for the industry, and then created Silicon Catalyst, which accelerates early stage semiconductor startups. And with Ramesh, we've been co-leading a Beyond Moore's Law initiative at Berkeley Labs.
Yeah, so I said to everybody at home, this was indeed a panel of experts, and I stand by that wholeheartedly here. So I'm going to direct my first question here at Jeff, and this is a conversation, so feel free, anybody at any point, to jump in and ask questions. But what do you think, Jeff, for you, looking at the semiconductor industry as a whole and what's coming, what are the most pressing issues to you right at the forefront that you say, man, my head is scratching, this is something we need to make sure we're paying attention to?
Yeah, I think it's probably two things that come to mind. One is, despite people talking about the death of Moore's law, the reality is we are continuing to push forward on that, and we need to continue to push forward on semiconductors and make sure that we continue to get high performance classical computing out there. And really the challenges there, besides the fact we're getting down to 2 nanometers, and is it the last announcement we made, is power and how we actually manage power and energy on these chips while continuing to shrink them, get higher densities and higher performance. The second part, though, I think is the burgeoning workloads in areas where maybe classical computing doesn't actually serve as well. So AI being right in front of us right now, but then quantum computing right behind it. Both of these are going to require a lot of the same semiconductor approaches we've used, but they're also require different approaches, different materials, different structures, different circuit designs and architectures on top of it. And I think that's it's really exciting because there's a lot more work to do, a lot of good chance for collaboration too along the way, but it's also really opens up the funnel in terms of the kinds of things you have to deal with.
So Dan, for you, do you agree with that assessment? I mean, that seems that's something when we talked about it earlier that you agreed with, of course. But from your opinion, how has that changed over the course of these last few years?
Well, Jeff's being modest. The roadmap for the industry actually looks really encouraging, both at the silicon level and as we try to stack chips and package chips of different functionality. We have a solid decade in front of us of I say, engineered progress to go. But that doesn't take away the clear and immediate danger that we needed to have already invented the next thing that comes to create the next S curve. And we haven't, or if we have, we haven't formed a broad consensus. So we're going to need unprecedented amounts of collaboration across from the university to the labs, and then scale those technologies so that the industry can adopt it. So while I've never been more encouraged about what's going on in terms of innovation and how it's addressing the workloads that are out there, we need to step up our game if we're going to be relevant. And I think Ramesh can talk about some of the challenges for energy efficiency that are in front of us.
Yeah, absolutely. So, Ramesh, the challenges for energy efficiency and the importance of collaboration. I think Daniel teed you up right there to really deep dive.
Right. So, little broad perspective, and this is very high level. I think there are 3 things that are changing dramatically because of all of the applications Jeff talked about. The total energy consumption, if you don't do anything to today's technology, total energy consumption by 2030 will be about 25% of primary energy. Today, it's about 5%, 6%. Nobody pays attention. They're worried about buildings and air conditioners and stuff like that. When it becomes 25%, you say, that's a pretty large amount. I need to do something. And the SRC folks have been, their decadal report basically outlines this. And therefore, at core, which is why we've been saying that the DOE has to be involved. Actually, that's the second part of the discussion, that at core, this is an energy efficiency question. At the same time, the exact same devices, which is why Sandia and all the national security labs are involved, the entire security apparatus is built around microelectronics. And we cannot, as a nation, afford to give away the control of that. That would be disastrous, I think. And therefore, that's a big driver for the United States. The third part of it is the size of the market. This market is no more today's number. It's going to be much larger. I mean, whether it is 3 trillion or 4 trillion is a moot point. It's a huge market. And we, as the United States, we need to have a stake in that market. We cannot give it away like we gave away the solar market to other countries. And that's why I think this whole notion of innovation has to come to the center in the sense that this country is amazing in terms of what it can innovate. We can out-innovate anybody given a challenge. And therefore, we need to find pathways by which the innovations can translate. Clearly, the national labs are a big piece. no other country, to my knowledge, actually many other countries approached us to copy the DOE national labs. And therefore, the national labs are a huge resource for everybody. It's your national lab, it's a taxpayer money going in there. So we could build the next phase of the semiconductor or the microelectronics ecosystem around these capabilities. Of course, the private sector is going to be the lead. People like Intel, Applied, or IBM are all going to be the key players. But I think the national labs are available for you. Actually, DOE just launched new funding, which is where I have to go next. But there is huge opportunities for you all to partner with the national labs and see what they can do. They have capabilities. LBL, I'll speak for LBL. We have synchrotrons, state-of-the-art synchrotron, perhaps the best synchrotron capability in the world. Computing capabilities that Peter was talking about. It's a user facility as well. We have the molecular foundry where we can make materials that nobody else can, and so on and so forth. So
I'll jump in too, because I remember spending many late nights at Stanford SLAC using the beam to try and try some of the strained silicon materials that we used to use.
Exactly.
And there's never been more use for that now. So it's a perfect partnership.
I think that it's also a good segue to Rick, because we were talking about this maybe in 2016, and we said we need to do something at the lab level. And so within the DOE complex, the labs have been working very closely with each other. And Rick and I, of course, triggered this, but everybody is participating. So with that, Rick.
Yeah, the work that we did a number of years ago was really around looking at broadly the capabilities at I guess we had 8 different labs and facilities involved. Mm-hmm. And across the whole spectrum of work, from materials characterization to device physics, simulation and validation, to component integration, all the way up into algorithms and software, and modeling power consumption of data centers. There are pretty unique capabilities existing at different laboratories at all these different levels. And the ability to pull those together and get access to capabilities that may not exist elsewhere in a commercially non-competitive way. It's really a unique thing that the labs offer. And almost all the labs have a variety of different vehicles for doing cooperative research together or other activities. And it's an unknown resource to a lot of things. I started out at Bell Labs, where I had lots of resources, but then I did startups for a number of years. And frankly, I really wasn't aware of these kind of opportunities. Now that I'm help running a facility that does silicon production and compound semiconductor production across 7 different technologies, I would have given my left arm when I was doing startups to get access to stuff like this. So it's a valuable resource, as Ramesh has pointed out. It's our tax dollars at work. So partner up.
So Daniel, from your perspective, as you've seen these partnerships develop, how do they really affect innovation, right? We're talking about how the need for energy efficiency and the need for innovation to be able to stay competitive at this global scale, but how do the partnerships feed into that level of information or innovation in your experience?
A couple things come to mind. First, just accessing these unique light sources and characterization capabilities so we can really understand what's happening to these materials and interfaces at the most basic fundamental level. So access to large investments that you would never make as a company or even a consortium for that matter. Two, though, is while that starts there, it's generally the collaboration with the lab scientist and the person seeking the help, where 1 + 1 is more than that. And so it's that interpersonal where you're working with a deep specialist. You can go way more beyond maybe the question that you're asking and fill in that level of detail. And then the third is there is a lot of industry research being done primarily through SRC, the Semiconductor Research Corporation, which really pools industry money and DARPA money and combines it and does leading edge university research. We can supplement that with a lot of the capabilities that exist in the lab system.
Yeah.
And so that's a big deal. And then the other major funder of early stage research is DARPA out of the Defense Department. And we've been working again to partner there to take what they're doing, but think of in further depth. And so those are the ways I see the collaborations working with industry, but also with the industry research organizations that have already been mobilized and are thinking ahead for what happens 10 to 15 years out.
Thank you. And I want to shift now to talk a bit into the specifics. The topic of this panel, right, is finding the future, right? And Jeff, I know IBM made that announcement beyond the 2 nanometers, a obviously huge deal and innovation, but what comes next? Can I leave it as generic as that and say, what's next? And I can throw that at the panel because I know that's the question everybody at home is asking too.
Right, well, I guarantee our marketing will continue the node naming down to 1 nanometer and beyond. But I think really the challenge is, and Dan touched on it, it's not just about shrinking devices. It's about how we're going to be packaging devices, hooking them up, different types of devices, because that's really the way you're going to get the same gains. We made the 2 nanometer announcement. We announced that it could give you either 45% higher performance or 75% energy savings. The fact that we always say both those shows you how important the energy savings part is, because a lot of people are going to use it for that rather than the extra performance. But to do that, it doesn't come because you shrank everything. It's because you did a bunch of stuff behind the scenes. So I think this effort to really think about the materials and device structures we need in the future are key. And that's where the fact that Ramesh mentioned that the DOE itself is now really getting into funding in the microelectronics space, which hasn't necessarily been the case in the past. But I think it's just a natural thing to happen. We've obviously collaborated with the DOE on the supercomputing side of things, right? The Oak Ridge Summit system that came out a couple of years ago. So they're one of the biggest consumers of these really high performance chips that come out. And I think they're realizing as well, if we want to keep those chips getting better and better, they're going to have to do some investment on the other side too. So we actually are building for the materials up to get the kind of structures we're going to need to keep that going.
Yeah. Hey, by the way, quickly to follow up what Jeff said, if you look at the 60 years, the focus has been on time scales or frequency. How fast can you go? What's the clock? Focus on length scales. That's why people go from 13.7 and now 3.2.1, all the stuff. I think the next version of the Moore's law is the energy scale. That's a third fundamental axis, going from picojoules. I mean, our program is focused on attojoules. How do you make things work? Still not at the quantum limit, but getting very close to that. And there is huge room there to innovate. And so you're going to see this progression of maybe half log scale or whatever it is of energy scales decreasing, which then at the systems level will lead to huge energy savings.
So help us put into context how big of a deal the energy efficiency of semiconductors are. We understand collectively as a group how semiconductors are in everything that we touch in our daily lives, of course, but what a lot of people don't realize is how much energy that takes. So as a group, can we help contextualize how important this is going to be moving forward in the future of designing and architecting these semiconductors? I'll throw it to Rick here since you made eye contact with me first.
So I think Ramesh introduced it. Right now, through Moore's law scaling and something called the NARD scaling, we've kind of gotten a free ride in continuous improvements of performance with no power, certainly for the first 30 or 40 years. The last 10 years, what we're starting to see is that well, you're not getting a free cell phone anymore, and the battery life is becoming a little more expensive. The main issue is that between the Internet of Things and sharing high definition videos, we're generating data at hyper exponential rates, and that has to be processed. The processing is not getting exponentially better in terms of energy usage. We are continuing Moore's law. We're scaling nodes. We're using more advanced packaging, but it's getting much, much harder. This is why we've seen this incredible consolidation in the semiconductor industry. And it looks like we may continue to see even more of that. It's an incredibly expensive and competitive business these days. So the bottom line is, if we want to continue the information era the way that we've been doing it, we have to find some way to stay on this gravy train. We've been doing it over the last certainly 5 years or so by adopting some more advanced packaging techniques, by doing some of these later node scales, although that's not readily available to everyone because it's very expensive. The other really big pole in this tent is special purpose processors or accelerator. So in the past, when IBM would build a large supercomputer for the DOE, it would be pretty much microprocessors, very, very good ones. But now these systems actually use microprocessors and graphical processing units. They use a heterogeneous combination of accelerators. That's probably going to, that trend will undoubtedly continue. And you heard in the quick pitches about some approaches. There's a variety of analog.
Did we lose Rick's mic there? Right at the point of your talk there, was that my sound? No, it's okay. We'll get you back, Rick, in just a second. So my question for Dan and Jeff and in the group here, what's the focus of the strategy? We all agree that it's important, but how do we as a country, what's the strategy moving forward to be able to ensure that these innovations are still happening?
I do think there is a lot of push right now, especially if you look at these special purpose processors, accelerators, to really have even more partnerships and collaborations. So obviously, we're talking here with the labs themselves. You can also see, the stuff we're doing, for example, in Albany with our AI hardware center, bringing lots of different industry players in. Whether it's even Intel now joining up with IBM on this, as well as a lot of the the materials and process and tools folks. And I think that that's going to be required. It's incredibly expensive to do this kind of research. And particularly if you're broadening it out to analog materials, resistive materials, all the stuff we heard about in the quick pitches and that we're working on across the board. There's a lot of research to do in different areas. So that means you need a lot of different people working on it and a lot of open flow of information. I mean, I think that's going to be, we see that in the software world, maybe more with open source software is already a main thing. I think we're going to see more of that kind of, let's raise all boats by getting the base technologies and science together. And then of course, we all can go make our own processes to go compete in the marketplace.
Has there been, you've all had these long careers throughout this. What would you say the magnitude of focus is on this compared to previous years? Is this at an all-time high? Is it something that's continuing to grow in terms of focus in on the need for this collectively in mainstream?
I think it's been growing. I think you always think it's as bad as it could be, but it always seems to be worse the next year. So I think there's always some new challenge out there that seems to grow as exponentially as Moore's law itself does, perhaps. So I think it's different only because it's not just about the scaling anymore. It used to be that we had a very clear focus as an industry. Scale it smaller, double the transistors, double the speed. It's all about speed. And now it's about, different types of transistors, multiple layers, get the energy down, figure out new packaging techniques. So the complexity certainly has gone way up, which makes, life in the fab even much more exciting. Like for people like Dan, when he was trying to manufacture stuff, it was hard enough in the past. It's even worse now.
There is perhaps, Dan knows this better. He was the president of Semitech. Semitech was created for another such event back in the early 80s because there was competition with the Far East, a different kind of a Far East, but nevertheless, there was competition. And so I think we could allude to that because, President Jinping, Xi has said, made in China 2025, So and they're investing not $5-10 million, $200 billion. So global competitiveness is at an all-time high, I would say, for so many reasons. And so I know this is why the CHIPS Act is so important. This is going to be the rallying feature for the entire U.S. ecosystem. And So we're very happy that the act is going through, and let's hope something good will come out of it.
And it really
strikes
comes
me-
back to the three pillars that that Ramesh introduced, that we evangelized 5 or 6 years ago. This energy security issue, we're seeing all kinds of impacts of climate change now.
Yeah.
The economic security issue is critical. I mean, the supply chains that we see are very, very delicate now. And then, you know, the national security aspects are critical. We fight with information these days, and that's only getting much more complex. And we need to have a very firm grounding on the reliability and the trustworthiness of the components that we get. So it was a compelling argument a few years ago. I think it's just gotten
even more compelling. Yeah.
I'll start with just an observation that while we're making great strides in machine learning and AI through deep neural nets, if you hear the accomplishments, whether it's machines playing games better than humans, or image and voice recognition, and on, but what's not generally described as how much energy went into training. We can drain a small town's worth of energy solving one of these problems, and the AI performance isn't doubling every 2 years like we knew in the semiconductor industry. It's doubling every 4 months, and so you just take the trajectory of our current CMOS technology and say, how far can we extrapolate that? And you realize we need the next thing, and so we need to ask, well, how does it feel? How we're going to work better at this? Well, we're going to need to invent new mechanisms that unite all of these capabilities, which are already focused on just getting through the next 10 years. But we need to double down on looking beyond that, what's around the corner, and it's going to be disruptive.
Yeah.
And in my experience at IBM, it was a lot easier to attack these problems because it was all within one company. And you could figure out how to optimize it, whether it was a new material or whether you were working on different system workload. You could work on that optimization as a company. Here, for good reasons, we've fragmented the industry, but now we have to pull it all back together again, because when something disruptive changes, well, it's not going to just drop into the industry infrastructure. We're going to have to, through startups and consortia and other mechanisms, we're going to have to be able to spin up new capabilities. So I think the CHIPS Act begins to contemplate that there's going to be a public-private partnership of some type to help pull this back together like we did in the 80s.
Yeah.
We're going to need to do something similar to that. And we're all on screen here, we're all talking about that and trying to figure out, based on what we've learned from the past, how can we take best practices and put it together in a workable mechanism? And that's not going to be easy.
Lindsay, I'm going to chicken out for the moment. Talk to you
Okay,
later.
thanks so much for joining us.
Yeah, so
We're going to put, Ramesh is speaking on another panel here shortly. We'll put that link as we wrap up in the next 2 minutes here or so. For those of you at home that haven't heard of the CHIPS Act, the acronym stands for Creating Helpful Incentives to Produce Semiconductors for America Act. So Senate Armed Service Committee included that in the defense authorization markup. So things are moving pretty quickly in terms of that act. But before we wrap up here with Daniel, Jeff, and Rick, I want to just ask you, what is your key takeaway? You know that the folks in the crowd today are all industry for the most part here. So what do you want them to take away from this conversation and for the future of semiconductors? I'll go around the horn here. I'm looking at you, Rick, first, and then we'll head down my gallery view. So what's your key takeaway for those in attendance?
I'd say that as we've discussed, the landscape's getting much more dynamic now. It's when I began my career, it was a little bit of the wild, wild west. You know, you couldn't actually make a fab in your garage, but you know, there were dozens and dozens of folks doing semiconductor fab and research and working at the leading edge. Moore's law, the great work in Semitech, it created a roadmap for the industry, and that gave a lot of predictability. We're entering a marketplace now where the technological challenges are introducing a wide variety of paths that can be taken. The international economic landscape and the national security landscape, it's driving uncertainty in all kinds of areas, making it very hard to manage a multi-$10 billion business, I'm sure. But it's one where if we want a strong position of in the U.S. economy and the global energy landscape, we kind of have to pull together and use all our resources appropriately. And the national labs are a large bucket of resources that should be tapped into.
Great, Rick. Thank you. So Daniel, same question. What's your key takeaway here? Your summary.
It's cool to be innovating in hardware again. It matters. And I'd like everyone to take away that it's up to us to recruit the next generation and show them how this is such a really important area and a fun area to work in. And that, just to build on what Rick said, is there was a bit of a monotony of just progressing through Moore's Law. We knew what was going to happen. We just had to make it happen. Well, we don't now. And I actually think that's a good thing because it's that much more exciting, and you don't have to just live in software to invent the next thing. It's going to be all about the hardware.
I wish that I had that quote. It's cool again to use in our marketing for this event. Let's put that on a poster. But thank you, Dan. And Jeff, your final thoughts, takeaways here for all the industry folks in attendance. What's the message they should leave with?
Yeah, I think actually Dan said it really well. Semiconductors are back, and I think you have to remember that semiconductors are what underlie everything. And I think in particular, it's not just that they run everything, but even for our economy, they're our number 1, 2, or 3 export every single year to the U.S. And that's been true for decades, and very few people even seem to realize that. So even economically, they have been incredibly important. So I think the fact that we're seeing the government really step out an investment here, and the DOE labs to say we're going to do microelectronics. The industry is pulling together in ways we haven't even before across competitors to go do it. The time is right now to actually see what's going to happen. And it's going to be driven for the next couple of decades because we got a long roadmap ahead through AI hardware, quantum hardware. A lot of stuff will all be built on semiconductors.
Yeah, absolutely. Well, thank you so much to our panel here for joining us. A few quick, just minor housekeeping things here for everybody. Please take just a moment to take our brief survey so that we can continue to make sure that all these events provide value to you, and reach out, info@bayarealabs.org. You heard it from Dan and Rick and Ramesh and Jeff, our fantastic expert panel today, just how important these sorts of collaborations and partnerships are to innovation in the semiconductor industry. Lastly, there is the Deputy Secretary of Energy is hosting a press conference right now as we speak. So we will put that into the chat. Make sure you head over there to see some great co-design opportunities and initiatives being announced today. So thank you once again, everyone, for joining us. On behalf of the Lab Innovation Networking Center, I'm Lindsay Maychek. Have a great rest of your afternoon and have a great day.
Thanks, Lindsay.